I'm going to try my best to make a video in less than 20 or 25 minutes. And what we're going to talk about in this video is probability. And I'll have to, I've had about 10 minutes trying to get my computer up and running. And so that's eating into my video making time because I've got to go off to my day job just as soon as I finish the video. So what we're going to talk about in this video is probability in R programming. So probability is a fundamental concept in mathematics and statistics that measures the likelihood of an event occurring. It provides a way to quantify uncertainty and make informed decisions based on the available information. Probability theory is the foundation of many statistical methods and plays a crucial role in various fields, such as finance, science, engineering, and social sciences. So the first thing we're going to do is we're going to cover some probability practice questions. So the first type of probability you have is classical probability. So classical probability is the ratio of the number of favorable outcomes to the number of possible outcomes. And then we're going to give you a practice question of you are rolling a standard 6-sided die. What is the probability of rolling a number greater than 4? So basically, there's two numbers in the die that are greater than 4, 5 and 6. So since 5 and 6 are the two numbers greater than 4, so that's going to be 2 divided by 6 is going to be your probability, or 1 divided by 3 is going to be your probability. 2 divided by 6, and you can break that down to 1 divided by 3, or 33%. But in order to solve this question in R, you see your die becomes 1 to 6. And then a probability of rolling greater than 4. Probability becomes sum, brackets, die greater than 4, brackets, length, die. So a sum of die greater than 4 is going to be, it's going to be 2. And length of die is going to be 6, so 2 over 6. And then you run the probability, and it's 2 over 6 or 1 over 3 or 0.333. So now we're going to discuss empirical probability. So empirical probability is another type of probability, and it's calculated by dividing the number of times an event occurs by the total number of trials. So you have a question, out of 100 light bulbs, the inspector finds 7 defective bulbs. Based on this sample, what is the probability that a light bulb produced by the factory is defective? Okay, so if you have 7 divided by 100 is 7%. But we're going to solve this question in R. So defective becomes 7. You got 7 defective light bulbs. Total becomes 100 out of a total of 100 light bulbs. And so empirical probability becomes defective, that's 7, divided by total, which is 100. And so that's 7 divided by 100, or 7%. So that is your empirical probability. So now we've got conditional probability. Conditional probability is the probability of an event occurring given that another event has already occurred. So we've got a practice question for that. Engineering has 60 employees, of which 15 are women. Marketing has 40 employees, of which 25 are women. If an employee is selected at random and is found to be a woman, what is the probability she is in marketing? So you got 15 over 60 is the women in engineering. So 1/4 is women in engineering. And you've got 25 over 40, which is the women in marketing. And so you've got more than 50% of women in marketing. So we're going to count that. So women in engineering becomes 15, women in marketing becomes 25, and then we're going to calculate the total women. So total women becomes women engineering plus women in marketing. So that's going to be 15 plus 25, so that's going to be 40. And then we're going to check the conditional probability. So probability becomes women in marketing over total women, because the question was about marketing. So women in marketing is 25 and the total women is 40. So it's going to give you a probability of 62.5%. So that answers the conditional probability question. So now we're going to talk about independent events. Two events are independent if the occurrence of one event does not affect the occurrence of the other event. And then we have a practice question to demonstrate this. So a fair coin is flipped twice. What is the probability of getting heads in both sides? So we're going to solve this question in two ways. The first way we're going to solve it is the R way, and the second way we're going to solve it is my way. So outcome becomes expand.grid brackets flip 1 equals C brackets H comma T comma flip 2 equals C brackets H comma T. So H is heads, T is tails, and you're going to create a vector because the C and the brackets means you're combining elements to create a vector. And then so we're going to measure the probability of getting heads on both flips. Probability becomes sum brackets outcome flip 1 equals H and outcome flip 2 equals H divided by n rows outcome. So you've got 2 rows. So that's your probability. So that's how you do it, the R way. Now, an easier way to do it is my way. So probability head 1 becomes 1/2. Probability head 2 becomes 1/2. Total prob equals probability head 1 times probability head 2, which is 0.25. So 0.5 times 0.5 is 0.25. So 1 divided by 2 times 1 divided by 2 equals 1 divided by 4. So my way is the easier way, but you can do it my way or the R way, any way you like. So the next thing we have is dependent events. Two events are dependent if the occurrence of one event affects the occurrence of the other event. A box contains 5 red balls and 3 blue balls. You draw 2 balls from the box, one after the other, without replacement. Because if you've watched my previous videos were talking about sampling with replacement and sampling without replacement. And most of the sampling we did was with replacement. But in this video, in this particular exercise, we're doing sampling without replacement. What is the probability that both balls drawn are red? And then so probability both balls drawn are red. You just don't need that. So to draw the first ball being red, it's going to be 5 divided by 8 because you've got 5 red balls and a total of 8 balls. And then the probability of second ball being red, and it's without replacement. So you've got 5 minus 1 equals 4 divided by 8 minus 1 equals 7. So you've got 4 divided by 7 is your probability for the second red ball. And so probability for both balls equals probability red ball times probability second red. And that's going to be 5 divided by 8 times 4 divided by 7. So 5 times 4 is 20 over 8 times 7, I think is 56. So it's going to be 20 divided by 56. And so if you divide that by 2, it's going to be 10 divided by 23, I believe. And then 10 divided by 23 is going to be 0.357. So now we're going to have theoretical probability. Theoretical probability is based on the assumption of equally likely outcomes. What is the theoretical probability of rolling a 3 on a 6-sided die? Is P3 equals 1/6. So the probability of rolling a 3 on a 6-divided die is 1 divided by 6, or 0.167. And then so you have all possible outcomes of a fair 6-sided die. So outcomes becomes 1 to 6. And probability of rolling a 3, P3 becomes sum outcomes equals 3, so that's 1 divided by length of outcomes is 6. So it's going to be 1 divided by 6, or 1.67. So now we're going to compare the theoretical probability to a simulation. So we're going to set our seed, and whenever you set your seed, every time you run the cell, it initializes the variables to the same values. So set.seed brackets 1, 2, 3. And then we're going to simulate 100,000 rows. So rows becomes sample brackets 1 to 6, comma, size equals 100,000, replace equals true. So this is going to be sampling with replacement. So empirical probability of rolling a 3, P empirical becomes mean, brackets, rows equals 3, and then your empirical probability is 1.6656. So this is a simulated probability. And so the one that we did before was theoretical probability is 1.667. And when we compare it to a simulation, it's 1.6656. And so this simulation, what it does is it proves the law of large numbers. And so basically what that says is if you perform a simulation, and you perform a simulation and then you run the test enough times, then what's going to happen is that test is going to meet the what it's supposed to be, basically. But we haven't covered the law of large numbers yet, but we will. So now we're going to do another practice questions, and it's going to be about candy bars. So your theoretical probability is based on the assumption of equally likely outcomes. It's calculated using the classical probability formula. And so we're going to have a theoretical probability concerning candy bars. So counts of each candy bar is Snickers becomes 6, Mars becomes 4, Milky Way becomes 5. Total equals Snickers plus Mars plus Milky Way. So 6 plus 4 is 10 plus 5 is 15. So you have a total of 15. So the theoretical probability of drawing 2 Snickers without replacement is P2 Snickers becomes Snickers divided by total. So that's going to be 6 divided by 15 times Snickers minus 1. So that's going to be 5 divided by 14. And then we're going to display the result. And it's going to be theoretical probability of drawing 2 Snickers. And so your theoretical probability of drawing 2 Snickers is 0.142. And so basically you're going to have the first probability is going to be 6 divided by 15. And then the second probability is going to be 6 minus 1 divided by 15 minus 1. So it's going to be 5 divided by 14. So you're going to have 6 divided by 15 times 5 divided by 14. So 6 times 5 is 30, and 5 times 14 is, I think, is 56. So it would be 30 divided by 56. Well, that's what it says, and it says it's going to be 0.14, but 30 divided by 56 is not that. I know that. So 15 times 14. So I got that wrong. So it's going to be 6 divided by 15 times 5 divided by 14. And then it's going to be 15. 6 times 5 is 30. And 15 times 14, which I don't know what it is right off the top of my head because I don't have a calculator on me. But it totals as 0.1428. So we solved the problem with the candy bars. So now we're going to study experimental probability, also known as empirical probability. It's based on actual experiments and observations. It is calculated using the empirical probability formula. And so we have a practice question. If a die is rolled 100 times and 3 appears 15 times, the experiment, so if a die is rolled 100 times and 3 appears 15 times, that means it's going to be 15%. The experimental probability of rolling a 3 is P3 equals 15 divided by 100 equals 0.15. So we're going to just do this in R. So the number of times 3 appears is count 3 becomes 15. Total number of rows is total rows becomes 100. And your experimental probability becomes count 3, which is 15, divided by total rows, which is 100. So it's going to be 15 divided by 100, or 15%. So the next thing we're going to talk about is subjective probability, and it's based on a personal judgment, intuition, or experience rather than on objective calculations. Suppose you assign subjective probabilities to the outcomes of a weather forecast. So you've got probability of sunny is 0.5, probability of rainy is 0.3, and probability of cloudy is 0.2. So subjective probabilities for weather outcomes is P sunny becomes 0.5, P rainy becomes 0.3, P cloudy becomes 0.2, and then we're going to combine them into a vector. So weather probability becomes C, you're making a vector, bracket sunny equals P sunny, rainy equals P rainy, cloudy equals P cloudy. And then you visualize that. So you've got sunny is 0.5, rainy is 0.3, and cloudy is 0.2. So if it's a subjective probability, you're not going to really perform any calculations because the subjective probability is based upon personal experience. And fortunately, I have finished the video in the time that I wanted to, so that's good. So now that I've finished the video, I'll have to go to my day job. But the next video I make is going to be a video on probabilities as well. So I hope that you decide to watch it.